Hey everyone. So the overall theme, aside from sanitizing threads, that I want to talk about today is, and the keyword for today is uncertainty. I think as programmers, we face uncertainty all the time. We deal with closed source APIs, such as UIKit, where as we've seen, sometimes the documentation says something different from the actual observed behavior. We work with large code bases where it's impossible for a single person to know about every moving piece. We deal with new and changing hardware requirements and different curveballs from Apple. And then sometimes we even have to build things to specifications using simulators before the actual thing is available. And we deal with a changing runtime environment with so many different combinations. We have users who are using our apps all around the world with different settings, different languages, different kinds of devices, different network conditions, operating system versions, and so on. So what is it that we can do to control uncertainty in our programming lives? That's the overall theme I want to talk about, and I'll come back to it at the end, but just keep it in the back of your mind as we continue on. And along the way, the motivating example and the practical thing that I want to talk about to explore the theme today is the thread sanitizer, part of the Clang compiler, and right there in Xcode as well. How many people have used the thread sanitizer, tried it on one of their projects before? Not too many people. Okay, maybe about a handful, 10 to 20 or so. Okay, sounds good. So I want to dig into the practical parts of the thread sanitizer, what it does, why you would want to use it, what kind of problems it will solve, and how it does it. That's the practical part. And we'll look at some really simple sample codes, some examples. We'll look at a little bit of dispatch queues, that kind of thing. And we'll understand a little bit better what kind of code the thread sanitizer will warn you about. There's a little bit of a parallel with test-driven development if you follow that. The usual thing is you write a failing test, you write the code, and then the test passes. Or if somebody files a bug, you want to write a test that fails to verify that the bug is there, then you want to fix it, and then you want to run the test again to make sure it passes now, to sort of make sure that you don't have any regressions. So similarly, when I'm looking at the thread sanitizer, I want to know what is the bit of code that I need to write to trigger the thread sanitizer to give me a warning, so that, and I think that'll help me understand a little bit better what it's doing and how it can help me. And then the meta point I also want to cover, as you can see with the reversed color scheme, that's the visual cue, is to see what can it teach us about writing better programs? How can we better manage the complexity of concurrency that we have to deal with? And how the thread sanitizer works, how can that teach us about how to look at and analyze our own programs better? So let's start with the problem statement. Here's a little bit of code. The code is going to run straight through, I would hope, and we should expect that it will print out 42. We set A to 10, we set it to 42, we print it out, very simple. Probably you can guess what's going to happen next. If we add a little asynchronicity to it, then it's not as clear. What's going to get printed out now? Is it going to print out 10? Is it going to print out 42? Is it going to print out something undefined? It's such a simple example, but even so, you can see what the problem is here. We have multiple queues. One is assigning a value to a variable, the other is setting a different value to the same variable, and then we're printing it out. And then maybe even the printing out is happening on a third queue. So in the first iteration of the code, the order of operations was clear. It's going to be the first thing, then the second thing, and the third thing. But now we have a little bit of uncertainty, splitting it up into different threads. Which line of code is going to run first? Which is going to run next? It's such a simple question, but without a clear sort of deterministic answer to it. So I'm sure you deal with code in your own applications, I would hope. That's more complex than this, probably orders of magnitude more complex than what you just saw. But just think, if we have this fundamental level of uncertainty about such a simple example, then how much complexity is there in an actual shipping application that you might be working on? Scrolling a table view, getting data over the network, that's already so much more complex than this. And I think that bringing the uncertainty of threads and threading in GCD and all that stuff to it just gives it a massive sort of exponential boost like this. That's not really exponential, but you get the idea. Let's look at a slightly different example. Here we're setting the value, and then we're reading and printing out the value from two different queues. How many people think that this code is a problem? A couple of brave people putting their hands. Maybe that's a bit of a trick question, because what do I mean when I say it's a problem? Certainly the order is going to change. Is the first one going to print out first, or is the second one going to print out first? We're not so sure. But the value itself hasn't changed. The value is going to stay constant as 88. So at least what is printed out and the value that's retrieved is going to be the same, and it'll be consistent. So there's no resource contention here. If this were a let instead of a var, we'd be even safer, because then it would just really be a constant, and then constants would be sort of inherently thread safe, and we don't have to worry about it. So if we take a step back now and look at the problem, we have a value, and we're reading it from multiple queues. And in this case, we're okay, because it's just going to keep getting the same value every time, and we're good. But if we read and write to the same value from multiple queues, then we run into problems. The order of operations now is important, and you can't be sure in a case like this sort of what's going to happen when and what value is going to come up. So this is how we've introduced the uncertainty into our program. So you've got your application, and you have some threaded code in there, and you want to try out the thread sanitizer. If you're in Xcode, all you need to do is edit the scheme and put a big check mark next to thread sanitizer and build and run, and then you're good. And note that thread sanitizer does have a compile. It has a build time component, and it has a runtime component. So that means if you look at this, you can still see that. It says requires recompilation, so it does need to do a full rebuild of your app, and we'll get into why and, again, how it works in a little bit. If you're on the command line, you can pass in sanitize equals thread for the Swift compiler, or it's fsanitize thread if you're using C or Objective-C. A few other caveats. It only works on 64-bit Mac, shouldn't be a problem these days, and it runs on the simulator, iOS and tvOS simulators. It does not work on device. And when you're running your app with the thread sanitizer, the documentation says there's about a 2 to 20x, which is a big range, 2 to 20x slowdown in sort of CPU time. And there's also an increase in memory usage of about 5 to 10x. So that's part of why you have to run it on the Mac, and on the device it would just sort of blow up right away. So that covers how to enable the thread sanitizer, but what exactly is it going to do for you? So let's return to this code here. This is, again, the example where we have two writes to the same variable, but from different threads, followed by a read. So if you have this code and you build it with the thread sanitizer, we're not sure about the order again. We weren't sure what it was going to print out. So this is, I would say, obviously a data race. So here's what you'll see when you run it. If you are on the command line, you'll see this. If you're in Xcode and you look at the debug console at the bottom, you'll also see something like this. So it's detected it as a data race, which is great. And then you can see exactly what the problem is. There is a write of size 8. That's 8 bytes because it's a 64-bit integer. So there's a write of size 8 by thread 1. I've got debug symbols on. It gives you the file. It gives you the line number. And why is this a problem? There was a previous read of size 8 at the same address on the main thread in this case. So this is the kind of detail that it'll give you. And it'll also tell you the location is this global variable A that you have. So you get all of those details there. If you don't like the debug console, you don't like reading too much, that's okay too. If you're in Xcode, then it looks much nicer. You get some error message here in the issue navigator. That's the 1, 2, 3, 4, 5th tab now. You're probably familiar with this already. This is where all of your compile errors and your link errors come in. But you'll see that there's this extra little switch here, like a segmented control, that lets you pick between build time issues and runtime issues. So if you use the thread sanitizer, that counts as a runtime issue. And it'll put the issues there and let you also navigate directly to the code. So you've got all of these same details here saying it's a data race, what the threads are. And then if you click on that line with the data race, the editor will switch to the file and open the file for you. So it's all very nice in Xcode. So that's what the thread sanitizer is going to do and sort of what kind of thing it's going to pick up. I'll point out one magical ability of the thread sanitizer here. So you've got your code and it's going off in all different kinds of places. You've got threads going here, threads going there, doing all kinds of different things. And remember, the problem it's going to detect for us is a race condition. You have some memory, a read from one thread, a write from another, and the problem occurs because the order isn't deterministic. We don't know if the write is going to happen before the read, or maybe you're like setting a property and you're setting a property, you're incrementing somewhere else and you're reading it from somewhere else, and then you delete something, and who knows what you're doing, but it just screams race condition. And if you had to debug a race condition, then you know how difficult it is to sort of catch it in the act. Because Who's had the experience where you see some weird behavior, your user reports some weird behavior in the app, and you see it, but then as soon as you plug it into Xcode and you run it in the debugger, it's perfectly fine. That's probably a common experience. I know that happens to me all the time. But because race conditions they have to do with timing, so often running them in the debugger with extra log messages and breakpoints, it messes up the timing, and a lot of times those bugs won't manifest themselves when you run them in the debugger, which can be maddening. So back to the threat sanitizer, and its superpower is that it can detect a potential race condition. So that means you don't actually need to run the threat sanitizer and have a race condition happen out there in the wild. The threat sanitizer will still be able to warn you about race conditions that could happen, even though they haven't happened yet. So again, I think that's sort of its superpower and the most amazing thing that it can do. So how exactly can it do it? We can dive now into the analysis portion of the talk. So just as threat sanitizer helps in analyzing our programs, let's dig in a little bit and sort of analyze the analyzer. So I've got a very simple Swift command line program in this case. We've got one integer variable, we're going to set it, then we're going to read it to print it out, then we'll set it again, and then we'll read it one more time to print it out a second time. So no queues or anything involved, we'll just run this straight through to see what it looks like. So again, Threat Sanitizer has a build time component, which means it has to recompile your app because it's adding code to your application. If you remember ARC, automatic reference counting, if you were around in the dark days when we had to manually retain and release memory, then you know when ARC was introduced, the compiler was going to add retains and releases to your code during the compilation step, and it was smart enough to know what to put where. So the Threat Sanitizer is doing something simple. It's injecting code into your application to track these kinds of things. So if you want to know what code Threat Sanitizer is adding, we could, of course, compile the app, look at the binary, but that's difficult to do and will probably lead to a lot of sadness. Maybe you've seen a diagram like this before, showing the different stages of compiling your Swift source code. You start with the Swift source code, you move on, you have a parsing step, move on to the abstract syntax tree, that's the AST, and so on and so on. So the AST is like a structured representation of your code. Imagine you got your Swift source code, but you turned it into like a tree-like structure. So it's just a transformation, it's not actually adding anything. So we need to look further down the line, not at the AST, but let's go one step down and look at SIL. That's the Swift Intermediate Language. So here's what I did. I ran the Swift compiler, Swift-C, from the command line, asked it to emit SIL, so not do the full compilation, but just go part of the way. And I ran it twice, once in regular mode like this, and then the second time with Threat Sanitizer enabled. And you can see I redirected the output to two separate files, and then I look at those files, and they are identical, no change. So that means that whatever the Threat Sanitizer is doing, it is not here, but it's further down the line. So it's not here. Maybe we can go one step down and look at the IR. That's the LLVM intermediate representation as IR. So let's follow the same procedure. Run the Swift compiler, ask it to emit IR, run it a second time, ask it to emit IR with the Threat Sanitizer enabled, redirect to two separate files, and this time you can see success. You can see that the IR generated with the Threat Sanitizer on is like double the size of the original. So that means that we could inspect the file, and maybe we could do a diff between the two and see exactly what code was added. So if you're reading IR, or if you haven't read it before, then that can make you as sad as reading that binary code before, but it's not so bad, so let's see what we can do here. So here's the start of our program. It's still at the top. You can see the defined entry point, and if you're a C programmer and you know what the signature of the main function is, then you'll see it here. There's like the argc, which is the argument count. It's an int32, and then there's the actual arguments, which is a character double pointer. Character is like an int8. So this is the main function. This is where the program's going to start. So we're good so far. And remember, the program itself was a equals 10 and then print a. So we'll scroll down a little bit and get to that part. So here's some of the code that sets the variable. Remember, it was a equals 10, a was an integer, so we're storing an int64 with the value of 10 somewhere. That's what that part is. And then the code will continue on, it'll do the print and print stuff out, but before we get there, let's peek at the Threat Sanitizer version. So when you compile with Threat Sanitizer on, you'll see an additional line inserted at this point, and it's calling TSan write 8. TSan is the Threat Sanitizer write 8. 8 means 8 bytes, because again, it's a 64-bit integer. And then we scroll later on down, and we want to print out the number. So again, Again, you'll remember that print takes a string. This is an integer, so it needs to do string interpolation, set up a string buffer, and so on. We can kind of skip that part. But we do need to read the value of the integer again. And so this is here, it's going to grab the pointer to the integer. It's going to read it, convert it to a string. And just as before, if we switch to the thread sanitizer version, there's going to be an additional call here, this time to TSan read 8, to say I had to read 8 bytes at this particular location. So that's the compile time addition. Every memory access is going to be preceded by these kinds of things. If you allow for a little bit of C++ code, and you're not going to get all angry, then let's go one level down again and look in what's going on. So we've got our TSan write function here. It's got 4 parameters. First one is the current thread, so it needs to keep track of what thread you're on. We've got caller PC, which is the memory address of whoever the caller is. So this is the code. We have the memory address that we're accessing, and then we have the size that we're accessing. So at its core, Thread Sanitizer tracks all reads and all writes to memory. So it's going to track what bit of memory, how much, from what thread, and from what part of the code. And so you can imagine a giant, giant list as your program is running and executing. There's this giant stream of accesses like this: thread, memory address, size, read or write. But once we have all that data, then what do we do with it? So this is going to just continue to grow and grow as we go. And then the question is, when do we have a race condition? When do we have a data race? So we have 3 conditions that all have to be fulfilled. There has to be an intersection of memory addresses, maybe, obviously. So if you access some memory over here, and then you access memory over here, then that's okay. That's not a race condition. It has to be on different threads. If you access the same bit of memory, but from the same thread, then that's totally fine. And at least one of them has to be a write. So again, if you read from the same location from many threads, that is also acceptable, but you have to have at least one write along with something else from different threads to the same bit of memory. You have to have all 3 of these together, and then you will get a data race. So that's the kind of thing that the thread sanitizer is going to pick up for you. We can review a little bit. So we started by thinking about uncertainty in our programs. We looked at threads and race conditions, looked a little bit about how to use the thread sanitizer, how to enable it, looked even into a little bit of SIL and LLVM code, and then sort of analyzed the thread sanitizer itself to see how it does its work. So now we can pop the stack, so to speak, and go all the way back to the beginning. And we were talking about uncertainty and how to deal with uncertainty in all of your complex code and complex projects. So the sort of underlying problem then is that when you have things running in parallel, it becomes more difficult to track what's going to happen when, and you need to think about order of operations and things like that. On iOS, we're already used to making certain calls on the main thread. That's sort of the, junior developer's way to fix anything. It's like, I'll just dispatch it onto the main thread and that'll probably fix the problem. But as we do more complex things like network access and image processing and things that take a long time, and we have to do these on background queues. We have multi-core mobile devices now, so we need to think more about concurrency and the complexity that it brings. So we've seen how the thread sanitizer works and the kinds of things that it can help you find, the kind of problems it can help you find. Let's sort of wrap up and talk about some lessons learned. So again, with the 2 color themes here. What are the lessons that I learned using the thread sanitizer, and what are the lessons learned by analyzing the thread sanitizer? So the first one, how to deal with uncertainty around threads, is obviously to run the thread sanitizer and sanitize all the things. So I definitely encourage you to try it out. Everyone who didn't put their hand up, edit the scheme, try out the app. A couple of caveats, of course, and a couple of issues you'll run into. First one is it has to be in the simulator. So if you have a camera app or something with AR or, I don't know, something advanced like that, then it may be difficult to do it in the simulator, but that's just a current limitation that we have. The second one is that it's not a static analyzer. If you've run the static analyzer and it comes with those cool diagrams with lots of arrows saying what leads to where, it is not a static analysis tool. You actually have to exercise the code. So the problem is you need to run the app with the thread sanitizer on in the simulator, and you actually need to hit the code paths that you want to test. So you have to tap on the buttons, fill in the fields, and do that kind of thing. So it is a little bit of manual work, or a lot of manual work, if you want to run the thread sanitizer and try things out. As a bonus, though, you can enable the thread sanitizer on your test targets. So if you have reasonably good unit test coverage, as I'm sure everybody here does, then you can edit the scheme for your test target, enable the thread sanitizer, and run it that way. And then as long as you have enough stuff in your unit test, or if you have end-to-end tests, or you have UI tests that will exercise more code, then you can also find a lot of threading issues thanks to thread sanitizer in tests. So the first thing is definitely you have to sort of find a place for the thread sanitizer in your life somehow, whether it's running it manually or running it with your tests. Next up, in terms of how to solve the uncertainty problem is, of course, just to become more knowledgeable. So a lot of times when I find, if the thread sanitizer finds an issue, the sort of number one fix more than half the time is just, I forgot to dispatch it to the correct queue. Either there's a callback and it's on the callback queue and I have to dispatch it, or the callback was on the incorrect thread, or there's some UI work on the main thread, that kind of thing. Most of the time, it's very easy to fix. Because of the information the thread sanitizer gives you, it says, thread 3 accessed this thing, thread 7 wrote this thing, and you can easily see what the problem is. So generally speaking, it's pretty easy to fix. You just need to put it on the correct thread. Other times, it's not so simple. If you have a concurrent queue, you have multiple things running at the same time, then it can be a little more complex. If you have a serial queue, maybe it's a little bit easier, because serial queues will just, as the name suggests, run straight through. But another thing to look into is a little more advanced GCD, so learning about things like target queues. If you have a concurrent queue and you have a serial queue that targets it, then the serial queue will run one by one, but as it puts the items onto the target queue, which might be concurrent, then they can run at the same time. So things like that are kind of things to learn about, or if you have them in your application already, it's to learn about a little bit further. And then the other thing to look at more is dispatch barriers. I was going to have a little live coding exercise or something, but I'll just skip over that. Dispatch barriers let you, I think the traditional example is a data structure. So if you have, again, concurrent reads is okay. The entire world, every thread in the world wants to read from my dictionary or whatever, perfectly fine. But whenever I want to write to the dictionary, I want to make sure that nobody else is touching it with a dispatch barrier, write to the dictionary, and then remove the barrier, and then let all the concurrent reads in again. So there are various strategies like that. There's all kinds of advanced stuff in Grand Central Dispatch to look at. So again, I encourage you to look at that stuff to sort of remove a little bit more of the uncertainty about how the system is working. Next up, we'll flip the color scheme. So collect the right data is also important to understand your program better. Again, to deal with uncertainty, you need to know, I guess the tricky part is you need to know what you don't know, but you also need to know what's available. So if we look at how the thread sanitizer works, it says, I need to know when this piece of memory is accessed from different threads and sort of at what time and in what order. And it has to know what data to collect. But it can't collect everything. It can't collect the source code, and it can't collect the entire state of the program. You have to make trade-offs. So if you look into a little bit more how the thread sanitizer works, it has things like a circular buffer, and it says I can only keep track of, obviously not every memory access in the world, but I can only look at the last 100 and so on. So there are trade-offs you need to do, and you need to decide what's the most important thing that I need to collect, and then how can I analyze that data to provide the appropriate warnings about data races and things like that. And the last thing is to go one more level down, so to speak. So if you want to sort of start an argument with your colleagues, you can ask them, how far down the stack do you think I need to know? And some people will say, you need to know storyboards and you need to know stack views, and that's all you need to do. And then the other grumpy person in the corner will say, well, stack views are based on auto layout, so you need to understand auto layout. And then somebody else will say, well, that's all based on frames. You should know how frames work. And then they'll say, well, you should actually know how the rendering works in core animation. And then somebody will say, you need to know how OpenGL works. And then the really crazy person in the corner is like, you should understand how transistors are made and how substrates work and things like that. And so I guess the point is there's always one more level down that you can understand, and wherever you think that line is of how much you need to know, operating systems, transistors, quantum physics, or whatever, there's always one more level down. So I always find that it's helpful for myself to say, I know iOS, I use the thread sanitizer, I want to understand a little bit more about how it works and to sort of dig down one level. Similarly, everybody knows and loves Swift, I'm sure. And it's like, what is one level down? Is it SIL? Is it IR? Is it understanding compilers? Is it understanding the standard library better? So I think it's important also as developers to learn and to, again, unpack some of the uncertainty that we have in our lives, is to not be afraid to go one more level down and sometimes to listen to that crazy person in the corner who's asking you to learn about compilers or whatever it is, because there is always more information there to learn and to pick up. And in the end, this is sort of the grand future that we want for ourselves, isn't it? Multiple threads executing in parallel, side by side, in total synchronized fashion, successfully accessing data with no data races. So I think this is the future that we all want for ourselves. So again, I encourage you to use the thread sanitizer, learn more about how it works, and hopefully along the way learn more about your own program and your own code so that you can understand it better and remove all of that uncertainty from your life. And that's all I got. Thank you very much.
Thank you, Greg, for the thread sanitizers. Do you have any questions from the floor?
I think I just stand here. Hi, Greg. My name is Kenny. I had to make a disclaimer. I'm not an iOS programmer. I have never written any Swift code before. But I think it's a great talk because as a programmer, most of the time, we always look at the code. Is my code thread safe? And sometimes we have a nightmare at 2 a.m. in the morning. Hey, oh, my code is not thread safe. Potentially some problem here. Yeah, I think your talk really gave us a good, really understanding how we can do better in iOS, in that development. So a little bit background on myself. I'm a compiler guy, so I'm probably the guy who sits at the back. Hey, you probably should read more about compiler. Okay, so I have actually a few questions, but I'm going to just ask two, okay, if I have time. The first question is that the example that you show that you only use simple integers with a var variable. But those raising conditions do happen in case you have using a let, so declarations with a variable, but on the right-hand side, you probably have more complex data structures. And even though on that level, it looks like, oh, that variable is immutable, but underneath, because it's a box value, and there's potentially like raising condition that might happen. So is the thread and sanitizer is capable enough to look deep down into the object on the right-hand side at runtime to figure out, oh, potentially there might be some overriding happening. So that was my first question. And my second question is actually a lot simpler.
Let me just answer that one, because I'll forget if you say your second question,
okay.
probably. No? The right-hand side expression would need to complete. So that variable that, even if you use let, the variable that you set, even though it's a very complex expression on the right-hand side, that will have to complete before anybody else can access the variable. So in that sense, the code later on that accesses it will not even reach until that's finished initializing itself. So if there's a race condition within the assignment or within the value on the right, then it would pick it up, but at least that value that you're setting will not be accessible until it's done. So at least there won't be a race condition in that sense.
Okay, so thank you. The second question is that does the thread sanitizer honor the lower operations such as compare and swap? Because even though that, potentially we have two threads actually writing or reading that particular memory address at the same time or some other time, it might collide and got into some trouble, but I'm actually using the compare and swap on a lower line, like so-called lower level of code. Like, I'm not sure whether the thread sanitizer is able to find, actually it seems to be okay here because I'm using compare and swap.
I don't know that specific example, but for some operations are marked as atomic in the runtime. Like if you did Objective-C in the old days and you had a property, you did atomic or non-atomic. If you have an atomic operation, those are detected separately by the thread sanitizer, and it will know that it's atomic and it's safe. So I don't know that specific example for compare and swap, but I would guess probably, yes. But I don't know for sure.
Thank you.
Thanks.
Do you have any more questions?
So, question, how does it work with GCD? Remember that we cannot be sure that, we have a serial queue, but sometimes this is in thread A, and then after that, another operation within the same serial queue goes to thread B and thread C and so on. Does it coalesce those things?
I'm sorry, if you have an access on thread A and another access on thread B?
Yeah, so if we submit a block to a serial queue, right? One block may go to thread A, right? After it finishes, the serial queue may decide, this one goes to thread B.
I see.
The next one go to thread C, but all of them were separated from the same serial queue. But theoretically, it should not be multiple access, right? So those kind of things like serial queues. How about serial queues that targets concurrent queues? Those kind of things.
Yeah, I see. I think sometimes probably I made the mistake in the talk as well, the difference between a thread and a queue. But it is GCD based, so it should respect the queue properly. Even if it's on a different thread, even if the queue owns multiple threads, it should be queue based. And so that example should work because it is the serial queue despite exactly what thread it's on. So I believe that will still work. Yeah.
Do you have any more questions? Well, okay. Thank you, Greg.
Thanks.